Yeah, it's nice to present someone else's result. That's welcome change. Okay, so this is some problem in Ramsey theory and combinatorial geometry. So Ramsey theory, this is some branch of combinatorics, which probably you all know, many of you. And you can think of it as sort of generalized pigeonhole principle. That's what I would think of it as. And it simply says that there are many results in combinatorics under this, what they call Ramsey theory, which says that if you have a large enough set of something in the universe, then if it's sufficiently large, then there's a large subset with a lot of structure. Yeah? And the particular problem here, this convex polygon problem, this is one of the, I would say, one of the original problems of modern combinatorial geometry. Okay? And it was also, it's very influential, this problem, because it initiated what we now call Ramsey theory. So there existed some Ramsey theoretic results earlier, but this was sort of the main starting point. Okay, so let me give you an example. And this is from the Erdős-Szekeres paper, this founding paper from 1935. And it says that if you take a sequence, let's say x1, x2, up to xn, these are real numbers, so real numbers, let's even say distinct. Okay, then there exists a subsequence. So this is really an ordered sequence of numbers. There's a subsequence, xi1, xi2, up to xi, let's say n plus 1. I have to write here n equals n squared plus 1. Okay, so you take n squared plus 1 distinct real numbers, order them in some sequence, whichever way you want. No matter how you do that, there will be a subsequence of length n plus 1, which is monotone. Okay, so that means that xi1 less than xi2 and so on, or, so that's increasing or decreasing. Okay, so this is sort of a very basic result. And it's simple. And this is described in the original paper. There's a more combinatorial way of viewing this, which says that if you take a partially ordered set, so this is a partial order, let's say finite. So you have a finite set with a partial order on it, and let A, this is longest anti-chain, or length of the longest anti-chain, and C, this is longest chain. I mean the length of the longest chain. Okay. Then A times C is always at least number of elements in the pool set. Yeah? This is a generalization of this observation here. Right? So simply you have your order here, the order in which the numbers are given to you, and if a guy is strictly less than a guy later in the sequence, you make a relation, right? Then he's less than that guy. Okay? Then of course an increasing sequence is a chain, and a decreasing sequence is an anti-chain. Yeah? And so the result follows. Yeah. So this is a generalization of that one. Okay, so now let me describe the polygon problem. So when I write ES, it means Erdős-Szekeres. Polygon problem. So first of all, let me say that a finite set in the plane, I'll always be dealing with finite subsets. So this is a finite subset. This is in general position. Position, this simply means no 3 on a line. Okay? And convex position means that they are the vertices of a convex polygon. Okay? So polygon. And the theorem they proved in their original paper was the following. So there exists a function. Let's call it f of n. So this is a function from the naturals. So the naturals with the property any f of n points in general position in the plane contains n points in convex position. Okay? And the polygon problem was to determine this f of n. So this is a Ramsey type statement. No matter, take this number of points, no matter how you put them in general position, there is some structure, there are these n points in convex position. You cannot avoid this. And in Ramsey theory, first you want to prove the existence of some regular structure. That's just proving the existence of this function, and then the secondary problem is to estimate that function as precisely as possible, right? And let's see, I'll write some bounds over here, I think. I can give you a proof, maybe. I'll do that here. So here is a simple proof. This is also from the original paper. So proof relies on two facts. First fact, among any 5 points in general position, there exist 4 points. Let's say general position. There exist 4 points in convex position. That's fact number 1. And fact number 2 is if every 4 points are in convex position, then whole set is in convex position. Both of these are very easy to show. First one, I'll give you a nice proof. Take your 5 points, they're in the plane, and for every pair of points, draw the segment between them. Okay? When you did that, you drew a graph. What graph have you drawn? K5. What do we know about K5? K5 is not a planar graph. So it meant that there were 2 segments that crossed. And they form 4 endpoints, and those must be in convex position. This is easy to check. Right? Now the second one, if you take a set of points in general position, you can triangulate this set of points. Take the convex hull. Like this. You can always triangulate such a convex polygon. There I made a triangulation. Yeah? Now if all of those points are not, if not all of them are on the convex hull, some guy is inside, and since I triangulated, some guy is on the inside of it 3 points. So there you found 3 points that are not in convex position. So if every 4 are in convex position, necessarily the whole thing must be in convex position. Now, with these 2 facts, I can immediately say that f of n is at most something called the Ramsey number 4 and 5. Now what does this mean? So this is one of the basic numbers of Ramsey theory. It says that there is some number, I don't know what it is, But there is some finite number such that if I color all the 4 element subsets by 2 colors, there will be a subset of size n or a subset of size 5, which every 4 element subset gets the same color. Okay? And how do I color it? Well, I color the 4 element subsets whether they're convex or not. Okay? So if I have this many points, either I get a 5 element subset where every 4 is colored by being not in convex position. That's not possible because of this one. Or I get n points where every 4 are colored as being in convex position, which means all of those n points are in convex position by this observation. Okay, so that gives you a bound that this is finite. Okay? So that's what they did in their paper. That's the first step they did in their paper, to prove that this function actually exists. And then, like I said, in Ramsey theory, then comes the question, how well can you estimate this? And in the same paper, they gave a different proof. Which they showed that f of n is at most 2n minus 4, n minus 2 plus 1. And this is roughly 4 to the n divided by root n, or you just write this as 4 to the n minus a little o of n. Okay? So I'm not exactly sure what this bound is. There are probably some estimates of it, but they don't know exactly what it is. But it's more than exponential. It's probably doubly exponential or something like this. Yeah? But their second argument shows that they can give an exponential upper bound. Yeah. And around 1960, the same guys showed that f of n, let's see, f of n is strictly greater than 2 to the n minus 2. And so this gives us a sort of divide in cultures. Some people say that the problem is solved. They showed that this Ramsey function is an exponential. Okay? But if you're more precise, you see that these are very far apart, right? Here I have a base 2, here I have a base 4. Right? So these functions are very far apart, but in much of Ramsey theory, one only cares about the order that this is an exponential. So already here you lost a lot of researchers who think that, so what? We know it's an exponential. But really one of the, I think, oldest problems of combinatorial geometry is to prove that this is the right number. In other words, so the conjecture is that f of n equals 2 to the n minus 2 plus 1. Right? If you take this many points, there must be n in convex position. This is also by Erdős-Szekeres. Very interesting, if you look in the literature, Erdős claims they never made this conjecture. Szekeres claims they did actually conjecture that this is the right thing. Erdős, some places, claims that they didn't really conjecture that this is the right function. So, but it's at least become known as the Erdős-Szekeres conjecture. Okay, and then, so this is a statement. This theorem here is taught in very many discrete math or combinatorics classes. So it's very well known. The problem is very well known. And many people have tried to make improvements upon this. And until last year, the only improvements that were made, and there were many improvements, were some multiplicative constant in front of here. So multiplying by some constant less than 1. Asymptotically, it doesn't change anything, right? The base is still the same. And I think, let's see. The first, okay, you guys can't see, but this isn't important. I'm not going to talk about this, right? The first, I think in the 1980s, Ron Graham and someone else managed to take this bound, so 2n minus 4, n minus 2, minus like n or something like that. right? But this was influential because it showed that you really can improve upon their argument. And then somebody did minus 5n. Somebody did 1/2 times that bound. And last year, 2 different groups managed to get maybe 1/8 of this or something like that. Again, just some constant, or 7/8 times this maybe. Reduce a little bit, and then what I want to talk about is Andrew Suk, about a month ago, announced a result. So maybe I should write that over here. Andrew Suk, this is the main result. So theorem, and this was posted on the archive 1 month ago. F of n is at most 2 to the n plus a little o of n. Okay. More precisely, what we'll show is 2 to the n plus n to the 4/5. Maybe there's a 4 here. Oh. Okay. So he has, and this is an asymptotic result, so n should be sufficiently large. Okay. But so really he has gotten the right base of this exponent. That's his main result. Yeah? So that's why I said this sort of this sequence of progress here. There are probably 10 papers reporting small sequences of progress, but they're so small compared to what he did that I don't think we should think about those anymore. Okay.
So
Yep.
the lower bound, they give a structure?
The lower bound is a construction. For every n, they construct a set of points. This many points, which has no convex n-gon. Yeah. Now, the research on this problem, like I said, it's a famous problem, and the goal, the hope, why someone would be interested in this problem is it should uncover some kind of structural properties about point sets, about large point sets. And Andrew's proof really does that, but in a sense he didn't discover any new structure. All the structural results he used were known for about 15 to 20 years. He just found the right way to combine all of these things. Okay? So what I want to do is tell you about these structural theorems. Okay, so the first one is an old one. This is the cup-cap bound. And this is also from the original Erdős-Szekeres 1935. And that's going to give this bound here. This is still very important. So the idea is to choose some horizontal direction and suppose that none of your points have the same x-coordinate. Okay? So you can order your points according to how they appear in this horizontal direction. And a cup, so a k-cup, once you've ordered them, is a set of points in convex position like this. Okay? And remember what I said about the increasing or decreasing sequence. This is related to that. A cap, sorry, this was a cap. And an L cup is like this. L points like this, and K cap is K points like this. Now how does it relate to these increasing or decreasing sequences? Well, here you should look at the slopes of consecutive ones. The slopes form a decreasing sequence. And here, the slopes form an increasing sequence. Yeah? So you're kind of dealing with the derivatives. Instead of just looking whether you're getting an increasing sequence, you're checking the derivatives. Yeah? That's what you should think of this as. And what they show is that, so here's a sort of simple claim, that if you have, say, a K cup, k cap, like this. And suppose the last point of that k cap is the starting point. So here is my cap, but that last point is also, the last point of the cap is a starting point of a cup. Okay, so let's call this cap x and let's call this cup y. Then x union y contains either a k plus 1 cap or L plus 1 cup. And it's very easy to show. But based on this, you can make a recursion. You can make an inductive proof or set up a recursion which eventually leads you to the following, that if you have k plus L minus 4, you know what, I'm going to use this later on, so I'll write it over here. Okay, so you make that observation that you can glue cups and caps together. It gives you the following: among any k plus L minus 4, choose k minus 2 plus 1 points. There exists a k cap or an L cup. Okay, so that's, once you have this, you set up the recursion and you get this out. Yeah. And this result is exact. So they also give a construction of this many points where there's no k cap, no L cup. Okay? So that is exact, and you get the bound that I told you for f of n by noticing that cups and caps, they're in convex position. So if you set k equals n and L equals n, you get the bound 2n minus 4, choose n minus 2, plus 1. Yeah? Now, and that gives you this 4 to the n exponential function. Yeah? But somehow you're losing something when you try to use this, right? And the reason is, suppose you have here a point set, and there's a convex n-gon inside here. You will typically not detect this as a cup or a cap, right? Generally, you choose some horizontal direction, only half of them will form a cup, only half of them will form a cap. Yeah? And that's exactly where you're losing this and getting 4 to the n instead of 2 to the n. And so somehow the key to trying to solve this problem, the polygon problem, is to find out how you can glue together cups with caps. Right? And this is what he figured out. And there's one more result I need to mention. This is called the positive fraction. Erdős-Szekeres, this is by Barani and Walter, published in 1998. And okay, now I might cheat a little bit. And I went a little fast. I want to mention one more thing about these cups and caps. Just, I told you there you should think of this as a generalization of the increasing and decreasing subsequence. And then I told you also that the increasing and decreasing subsequence is actually a consequence of a general combinatorial statement about partially ordered sets, chains and anti-chains. And it turns out that this is also a consequence of such a combinatorial thing. So what you do is you take a 3-uniform hypergraph. And you complete 3-uniform hypergraph with ordered vertices. Okay, so you put a linear order on the vertices, 1 up to n. Okay? And a coloring, so I'm going to color this hypergraph with 2 colors. Okay, so 2 coloring of the edges is transitive if the following holds. So you take a triple And suppose this was colored red. Yeah? So I, J, K. Now suppose the two last ones were the starting point of another triple. So here's I, here's J, here's K, here's L, right? And suppose JKL also is colored red. Then I say the coloring is transitive if all the triples formed by these four are colored red. Yeah? So if this triple and the next triple is red, then the ones in between are also red. So these cups and caps, they form precisely this. So I'll color it red if these three form a cup. And if the next, starting at this one here and this guy is a cap, then the ones in between are also caps. Yeah? And so it turns out you can make a purely combinatorial proof saying that if your hypergraph has at least that many vertices and the coloring is transitive, then there is a complete red subgraph of size K or a complete blue one of size L. Yeah? So really it's not much geometric considerations here, it's just this transitivity is important. Yeah. So that's the combinatorial version of this cup-cap theorem. Okay, so now I go on to the positive fraction, and this is a structural result about points, planar point sets in general position. So here's where I need to cheat. It's a bit long. Okay, so for every integer k, say at least 3, there exists an epsilon, which is positive. This is a real number, such that if x is a finite set, general position R2, and let's say x is at least, this is the Erdős-Szekeres function, okay, so it's big. It's big enough so that it contains convex k tuples. Yeah? Then there exists x1, x2, xk. These are subsets of x. Each of them is large, epsilon k. So each of them contains a positive fraction of the whole point set. Yeah? Such that every transversal, which means y1 and x1, yk and xk, is in convex position. So this is a special case of something very general that appears in discrete geometry. These kind of positive fraction results. Okay? It's very powerful, but for this problem, it was Andrew who discovered how to really use the power of this. It's been used for many other things, not exactly this one, but sort of variations of this. The fact that there are these positive, you can partition, or it's not partition, but you can find large subsets. Sorry, these are distinct, disjoint. I'll make a picture to show you what this means. This is a special case of something more general called the same type lemma, which says that you can find large uniform substructures in sets of points. This in any dimension and so on. Uniform means that you can find large subsets. They should be a positive fraction of the size, and no matter how you sample a point from each of them, any sample captures the entire structure of what's going on. So it's invariant over which points you choose. Right? This does not happen in general in combinatorics for hypergraphs, but it's something special that happens for point sets. Okay, so what does it mean? It means here is my big point set. Yeah, that's everything. Inside here, I can find a little cluster of points here. That's x1, x2, x3, x4, and so on. Yeah? And the fact that every transversal is in convex position means that for each of these, I can find a line that separates this from the other guys. Like that. Okay? So all my points are clustered here. Not all my points, but the important thing here is that each of these is large. It's really a positive fraction of the entire thing. Right? And here is, we're dealing with exponential size sets, right? So, yeah.
Can you just, so the epsilons, what are they like?
Oh yeah, I'm gonna,
Oh, sorry.
no, it is important. So originally they just proved that there is some epsilon. It was improved a little bit by someone. And then Poor and Walter showed that epsilon k is at least, so this is going to be used in the proof, 1 over 2 to the 32 k. Okay? Andrew is only using the fact that it's 1 over 2 to the c times k. I think he's going to use to simplify his computations like this. This is smaller than that, so you're fine.
Are the clusters transversal or the points are?
No, a transversal means a choice of 1 point from each of them. That's what a transversal means. So it just means any representative you choose, 1 from each of them, they will always be in convex position. But this, you need to think about it, but it forces precisely this structure here. In fact, yeah, so you extend these lines, you get these regions, and the cluster must lie inside these regions. Yeah?
Is this somehow related to regularity lemma?
Yes, it is a type of regularity lemma, yeah.
And this was restricted to the two-dimensional case?
No, not at all. So there's something called more general, called the same type lemma, which says that you can, given any set, you can find large subsets, and any transversal has the same order type. Yeah. And so this is, yeah, it's something very specific that you see among point sets. Regularity means that there will be some error inside here. But you can bound the error. But what happens in real point sets is that there's actually no error at all. Really, everything here represents the same thing. Yeah. Any transversal. Okay, so it's not a very hard theorem actually. So I'll show you how this Poor and Walter proved this. So the original proof of actually the more general thing I told you is based on the ham sandwich theorem. So you just make cuts and cuts and cuts by ham sandwich and it comes out. I'll not do that because we actually need this estimate here. I'll erase his theorem. Okay, so I'll give you a sketch of this, so a proof sketch. So, 1 second. So let n be large. N is my number of points. I have n points, and n is going to be greater than 2 to the 32k. Large, okay? Greater than. Okay. Now I know that among any 4 to the 4k, there exists a convex 4k tuple. Right? That's just the original Erdős-Szekeres theorem. Yeah. Okay, so the point is now to count these. Okay, so I do a double count. And this is a simple double counting, tells you that there are many convex 4k tuples. Okay? And choose 4k divided by 4 to the 4k, choose 4k. So at least this many convex 4K tuples. Okay. So that's just a double counting. Now once you have a 4K tuple, which is convex, then if you mark, here's a definition. You mark them alternatingly, like this, and I'll say that these four support that 4K tuple. Okay? Meaning each convex 4K tuple has two supporting 2K tuples. Okay? Either these or these ones.
Can you go back to this double counting? Is it?
So you take n, choose 4 to the 4k. Every time you choose 4 to the 4k,
Yeah.
you see a convex 4k tuple, at least one.
Right.
And then and each 4k tuple, convex one, is contained in n minus 4k.
N minus 4k
Choose 4 to the 4k minus
4k.
yeah,
I see.
and you rearrange and you get this. Okay, so once I have a convex 4k tuple, I say that it gets supported by this 2k tuple, right? And there are two ways you can support it. Yeah. Now, how many 2k tuples are there in total? So it means that I have this many convex 4k tuples. So it means that n, choose 4k, 4 to the 4k. So I divide by n, choose 2k. Okay? This is an averaging. So it means that there is some 2k tuple that supports some 2k tuple supports this many convex 4k tuples. Yeah? So some convex 2k tuple supports at least this many 4k tuples. Yeah? That's just averaging. And so you fix one of those. Now this is the one. I fixed it. Now this convex 2k tuple, it forms regions R1, R2, R3, R2k. Yeah? And every time I see a convex 4k tuple, I see a point here, a point here, a point here, a point here. Right? In addition to those guys who are supporting it. Yeah? But of course, one 4k tuple could look like this, and then another one could look like the same point, a different point, and the same point. Yeah? Those are counted separately. So let's just say that here there are T1 points, right? Here I get T2, T3, T2k. So you just record these, how many points you see in each of these regions. Okay, so the product of these Ti's. Here I need to do some estimate. This is going to be greater than okay, so here you need to do your estimates of binomials and so on. Okay? You'll get that there are at least, there's a 2k tuple that supports at least this many things. Yeah? Okay. Now this number here is of course a lower bound on the product of these Ti's. Yeah? And then comes the final trick, is that the product of these Ti's is less than or equal alpha to the k times n to the k, where alpha is the kth largest Ti. Okay? So you've taken the product of these two k numbers. You take the middle value, replace all the smaller ones with that one, and you replace all the other ones with this obvious upper bound. Yeah? And then you do the calculation, you solve for k, and you get this lower bound. I'll skip that. Yeah? But that's the whole proof. And of course, these things getting supported are precisely in the position I want.
So alpha to the k, why is it?
I have a product of 2k numbers here, x1 to 2k.
Right.
And you replace, I want an upper bound. So say they're in weakly increasing order. Of course, I don't know the order they appear in, but so just replace these guys by that number there. You get something bigger.
Smaller ones.
The smaller ones you replace by that one. And then the next half you replace by the maximum they could be, which is n to the k. Or n, sorry, n, yeah. So it's very simple averaging principles, all of this. Yeah? Okay, so that gives us the positive fraction version. So now I have 15 minutes left, so now we can see Andrew's proof. How does he use all of this? Let's see. Yeah, I'll delete this sketch. Now, like I said, the key to improve on this problem, and this was sort of known, is that we know how to get cups or caps. The way we could improve on this is to find out how you can find a cup and combine it with some cap such that they form something that is convex, right? That's sort of the whole key. And that's what he figured out using this structure. Okay, so he's going to prove f of n is at most... Okay, I'm going to skip using floors and ceilings. Okay? 2 to the n plus 4 n to the 4/5. Something like this. I'll set this equal, I'll call this capital N now. And so, first step, apply positive fraction Erdős-Szekeres with k equals roughly root n. Okay? So I have square root of n regions here, clusters, yeah? As in this picture here. I'll just call these regions R1, R2, up to here, Rk. K is square root of n. There might be a +1 or +2 or something. It's not so... I'll do it a little roughly here, right?
So here we're applying the classical bound.
Here I am applying... No, I'm applying this theorem. I'm setting k equals root n. Okay? And this point set has this size. Yeah?
We need to know that that size is larger than fk.
Actually, you don't need that, right?
You don't really need that. If you take floor here, this will become 0, right?
Oh, yeah. Right.
I mean, you don't really need... no. Just that when... Right, so when this number here times the size of n becomes greater than 1, you're guaranteed 1 convex k-tuple, right? And then it just says that there's this concentration phenomenon. Yeah. Okay, so k is set to be root n. So this means that each of these regions, or clusters, Ri, has size at least n divided by 2 to the 32 and half. He says 50 here. There's no danger in that. Okay. But you can see how this is going to be very useful. Suppose I wanted to not be as ambitious as Andrew and get 2 to the n plus this little O of n, but I wanted to improve on the 4 to the n, so suppose I took 2.1 to the n, right? And then I apply this fractional version. I get a positive fraction of 2.1 to the n. It means that inside each of these clusters, I already have much more than the conjectured value, 2 to the n, yeah? Since it's a positive fraction. So that's the power of this positive fraction results, is that you really pick up a lot of stuff in each cluster. So now I have a lot to work with. And then you can really go even a little bit below here, like he did, if you do the estimates tight here. Okay. Now inside each region, so here is a region, Ri. Remember, I'll draw them with red so you can compare with the picture over there. Right, there's a line, and it has these boundaries like this. Yeah? That's what a region looks like. Now inside each region you make a partial order. Order, that's fine. And the way you do that is as follows. You take these endpoints, and I'll say that x is less than y if, let me call these endpoints v and w. X is in the convex hull of v, w, y. Okay? So I have a point here. This is x. X is below y in the partial order if the triangle spanned by these bounding vertices like this. Yeah? And for example, z here, let's see, z is above x, but z and y are not related. Yeah? So that gives me a partial order. And you make such a partial order for each region. They're independent of each other. Okay. Now, set alpha equal n to the minus 1/5. Then we have the following. Each Ri contains let me see, right, contains either an anti-chain AI where the size is at least, sorry, Ri. I'm using Ri for the set of points in the region. Yeah? Times to the power alpha, or chain Ci, the size of Ci, okay, so this is the first or second theorem I mentioned, right, about the width and the height of a partial order. Right, the longest chain, the length of the longest chain times the length of the longest anti-chain is at least the number of points there. Yeah?
Do you really want to make alpha to be n to the minus 1 over pi?
Yes, I do.
Okay, I mean,
Yeah.
it looks like you may want to choose alpha as some.
No, I want to choose it this.
Okay.
Yeah. Okay, so in either case, I say this is a big anti-chain, this is a big chain. Yeah? And yeah, so here comes another step with some estimates. I'll write them here. Ri to the alpha is at least. Okay, so here I'm again skipping ceilings and floors. So a large anti-chain, it's like this, and this is going to be at least, so then you plug in your numbers. You know the size of the total point set. You know that each of these clusters contains a positive fraction of that. Yeah? And then you plug in for these values, and you see that this, I'll write it out. 3/5. And so here, I'm sure you could make some small improvements if you were very careful. Yeah? I don't know if it's worth it. And then you want to use some estimation of binomial coefficients. So what does this look like written as a binomial coefficient? That's the key. This is at least n plus 2 to the 2n to the 3/4 minus 4. Choose n minus 2 plus 1. Ci, which is at least size of Ri 1 minus alpha, n plus Okay, so here you should use some estimates on binomial coefficients. Okay, so the first one, this fraction of the total point set to the power alpha is going to be at least this binomial. The second one, the fraction to the power 1 minus alpha is going to be at least this. And here's one trick. Here you have a range of i's you can choose here. Okay, I can vary here as integers between 1 and n to the 1/4. So you should maybe put a ceiling here or a floor to make these integers. Okay?
You mean you can choose any I or you
Any I. Any I. For any I in this range, this estimate will hold when n is sufficiently large. Okay, so he has this thing that n should be sufficiently large. Okay? And so I'm not going to give the calculations of these estimates. That you can figure out on your own. This is the key. But it's in a kind of nice form here, right? That's why I put it here. Here you have something plus something minus 4. Choose that something minus 2 plus 1. It looks kind of like this. And here you have something plus something minus 4. Choose something also minus 2 plus 1. Also kind of this form. Yeah? So that's, we're going to use that. Okay, so let me delete the statement of this positive fraction. So now the proof divides into two cases. So case 1. All right, so let's look at this picture again. I have my root n clusters, right? Each cluster I now mark. All right, so I mark each cluster. Maybe I'll mark this one A, C, C, etc. according to which one was big. In each cluster, I know that either there's a large antichain or a large chain. So I just mark them. Yeah? So I get this circle of A's and C's. Yeah? Okay. So once you've done that, you have case 1. There are at least n to the 1/4 antichains. So large antichains. Yeah? Or case 2, at least n to the 1/4 consecutive. So this is another trick. Consecutive chains. Okay? Total number of things here is n to the 1/2, right? Either you have n to the 1/4 antichains. If there's less than that, then there are very many of these things are chains. So in particular, there will be a consecutive, so on the circle here, there will be a consecutive string of this length, all with chains. So this is just pigeonhole principle. Yeah. Okay. Now let's deal with case 1. So among these n to the 1/4 antichains, there are at least non-consecutive consecutive antichains. Yeah?
Choose every other
Yeah,
one?
choose every other one or something like this. Yeah. Okay. And then now I need a little picture. Okay, so what did it mean that it was an antichain? I maybe didn't focus on that enough. It means that two guys in an antichain, look at the line they span. Okay, this line will intersect. So each region is formed by a base and two boundaries like this. Now, the elements in an antichain, any two guys in an antichain, the line that spans them, they intersect the two sides before they intersect the base. Yeah? Okay. So, in particular means that if you look at two guys in an antichain, look at the line they span, they never intersect. They might intersect this region, but if you skip one, they won't intersect this region here. That's why I'm taking non-consecutive ones, okay? So I have a region here, I skip one, maybe here, right? So the line spanned by these two is not going to intersect any of these other guys. Okay? Now in each one of these, I now order my point sets according to this direction. Okay? And I have many points inside there, right? This is anti-chains, there are at least this many. So either there is an n cap, so inside this region there's either an n cup, then I'm done. If there's not an n cup, there is a 2n⁻³ cap. Yeah. Now the beauty about skipping these is if you take a cap inside here, remember these lines never intersect this region, so there's also a cap here and a cap here, and you can glue them together. Yeah? So there are, if any of these has a cup, I'm done, n cup. So each of them, let's assume, has at least that long cap, right? So how many of these are there? There's 1/2 n⁻⁴, and each of them has a cup of length 2n⁻⁴. So you can glue them together and you get n guys in convex position. Yeah? So that's case 1. And then case 2, I'll delete here. So case 2, we have these consecutive chains. Okay. So let's look at two consecutive. Yeah.
I'm sorry, but I'm confused. So there is n cap or 2 times n⁻⁴ cup, right?
Yeah, or you can, delete here so that becomes cup and add something here and becomes cap.
Yeah.
It's kind of symmetric, yeah?
Sure.
Yeah. So, okay. So now we look at two consecutive chains. Let's suppose this one is, so R1, R2, etc. Okay, so you pick out your consecutive chains. And now I'm going to order them differently. So in the first case, I ordered my point set now according to this order. Now I'm going to order my point set here with the order, take its right bounding vertex, yeah, and order as you sweep this way. Okay? So your points are here, they're forming a chain, and you get some order of them like this. Now, what you need to check is that so the order you get here on the next one, it's the same, or the reverse rather, if I were to extend these this way. Okay? So when you sweep a line through this vertex, you're ordering these guys. You're also ordering these guys. Yeah? Like this. But what you're getting is essentially the same order as if you swept here. And that's using the fact that these are anti-chains. If they're chains, you cannot do that.
But they are chains.
Sorry, you're using that they are chains. Yeah. Yeah. All right, so that's where this divide in the very beginning, filtering out the chains or the anti-chains, was important. Yeah? Okay, so that's one observation. But now I have an ordering of my points. And then, like I said, this cup-cap theorem is not really about ordering them along the horizontal axis. It's just some total order on your vertices. And then you can define these cups and caps and transitive colorings. Right? So a cup would simply be something that, let's see, if I take 3 from this order, the guy in between, you need to pass through that triangle to get to him. Yeah, that's a, I'll call that a cap. And if it was inside here, that's a cup. Yeah? Okay, so again, I have cups and caps. This is a transitive, gives me transitivity, so I can apply the abstract cup-cap theorem about transitive colorings. Okay, so let's look at region 1. And let's put I equals 1 over here. So what does it say? It says that either there's an n cup or an n to the 3/4 cap. Okay? If there is an n cup, then I'm happy, I'm done. Right? So there should be a cap of length at least n to the 3/4. Okay, now I go to the next region. So in this region, there is either an n minus n to the 3/4 cup, call that cup, oriented from here, or a 2n to the 3/4 cap. Yeah? I had a table written in my notes. Maybe that's not so bad to... So here, in region 1, you have either n cup or n to the 3/4 cap. In region 2, so the next one, n minus n to the 3/4 cup or a 2n to the 3/4 cap. Okay, so you have something plus something which always is going to equal this number here. Yeah? That's why I have this I here. Yeah. Or 3 will have either n minus 2n to 3/4 cup or a 3n to 3/4 cap. And all the way to the last guy, which was roughly n to the 1/4, right? Yeah. Which either has an n to the 3/4 cup or n cap. Yeah? Okay, so now let's look at this situation. I'll draw one more region here. Okay, so if there's an n cup in region 1, I'm happy, I'm done. Yeah? Okay, so let's suppose that doesn't happen. I'm here. So here's my... There. Okay, now I go to region 2. There's either an n minus n to 3/4 cup. But here's the next nice thing. A cup on this side can be glued to that one.
Okay.
Yes? So in this case, again, I'm happy because I had this case. So I may assume I have this one. Right? So here, well, this has length 2 times n to 3/4. Either there's a cup that I can match up with this guy, or there's a cap. And in the end, you close it and you get what you need. One of these happens. Yeah? All right, sorry. Either you get this, or you end up here. And that's the proof.
Wow.
Yeah.
Yeah, that's it.